This unit has been all about exponential functions. Um, and the first couple days are just kind of going over what exponents are, what kind of properties exponential expressions have, how to write exponential functions. But starting last time and kind of moving forward to today, and even the next time I'll see you, we're going to look at applications of exponential functions. So last class we looked at exponential growth and decay, mostly talking about population growth and how populations can also decay over time, but also some other examples of things behavior that can be modeled with an exponential function. So today we're going to look at another application of exponential functions, and that is the idea of a half-life. So this is something you may have talked about like in chemistry maybe, but I'm going to try to put a little algebraic spin on this. So basically what a half-life is when you have a radioactive isotope, it decays at some rate, okay? And the half-life is a measure of time that it takes for that substance or that isotope to decay to half of its original amount. So for instance, if you had something that had a half-life of like 10 days, let's say you started with 100 grams of it, after 10 days, you would have only 50 grams of it. And after another 10 days, you'd have only 25 grams of that. After another 10 days, so basically every 10 days, you would cut the number in half. Now, every isotope has a different half-life, meaning like some decay faster than others. So part of this is kind of getting into what you don't have to memorize any particular isotope's half-life or anything. That'll always be given, but that's going to come into play when we start writing the equations. So they're all going to come back to these exponential functions, which, if you remember, are generally written as y equals a times b to the x, where a was your initial amount and the b was your multiplier here. Now, what we saw in the last lesson is that if you're growing at an exponential rate or decaying, and you're growing by or decaying by some percentage, then we would have to figure out what that multiplier is by either adding or subtracting that percentage from 100%. So it'd be like 1 plus the rate or 1 minus the rate. But here the multiplier is just going to be the same every time. It's just going to be 1/2 because you're cutting the number in half. But what's going to be a little bit different is the x value here. Because since every half-life is different, since we are measuring the number of half-lives rather than the number of years that go by, we're going to have to divide the number of years by whatever that half-life is. So we figure out how many half-lives have occurred. So I'm going to break down the formula here for you for a half-life. And this formula can take some different forms. So, not in this class, but maybe in a future math class, you might come across a half-life lesson where they write the formula a little bit differently, and that's okay. I've definitely seen this presented in different ways. Particularly, sometimes they use Euler's number as the base. But I think it's a lot easier to sort of like understand it contextually if we have 1/2 as the base. So, all that said, let's break down the formula here. Now, again, your generic exponential function is going to be a times b to the x. But for this half-life formula, we're dealing with different substances, and the output will be however much of it is left after however much time goes by. So I'm going to write it like this. F, that's going to be our final amount, equals capital A, that's going to be our initial amount, times 1/2, that's our multiplier. And then really the only sort of like gimmick part of this, where it's like a little different than some of the other exponential functions we looked at, is we're going to take the amount of time and divide it by however long the half-life is. And that's because something that's different about these kind of problems is the x in the exponent is not going to stand for how much time has elapsed, but rather stands for how many half-lives have occurred. Okay, let me be pretty clear about this. So this little fraction, that's the exponent on the 1/2. That represents the number of half-lives that have occurred. So just to give you like a kind of a simple example to kind of process that, let's say the half-life was 25 years, right? And let's say we're measuring this thing over the course of 100 years. So 100 years go by, each half-life occurs after 25 years, there would be a total of 4 half-lives that occur. Now, just happening once every 25 years, over the course of 100 years, you'd have 4 of them. And so when we divide the total time by the length of the half-life, that's what we're computing, is the number of half-lives that occur. So just to break down each of these variables, the capital A stands for the initial amount. The F is the final amount. The T represents the total time that has elapsed. Or gone by. The H is the length of the half-life. And this T over H is computing, like what I wrote up there, the total number of half-lives. Again, like the example I was trying to describe earlier, if the half-life is 25 years and 100 years go by, that means there's a total of 4 half-lives occurring. 100 divided by 25 is 4. So you don't have to necessarily memorize this formula. I'll give you this formula, but you do need to know like where all the numbers go. You need to be able to plug in the numbers into the right places and be very clear about what it is you're solving for. So any questions so far? This kind of seems like it's turning into a chemistry class here, but this is just one of the many applications of exponential functions. So let's take a look at example 1. It says fluorine has a half-life of 11 seconds, so it decays very quickly. Find the amount of fluorine left from a 40-gram sample after 44 seconds. Okay, so sometimes, like if you just think your way through the problem, you can figure it out even without the without using the formula. And I kind of want to go through that thought process here, so you can see kind of how you could figure it out without the formula. But also show how the formula can compute it maybe a little bit easier. So let's just kind of keep track of the number of seconds that go by and how much is left over. So since we're starting with 40 grams, if 0 seconds go by, we have a total of 40 grams, right? Now the half-life is 11 seconds, which means that after 11 seconds, you're going to have half of what was remaining. You're basically going to multiply that amount left by 1/2. That's your multiplier. So after 11 seconds, we should have 20 grams left over. It's half of 40. And then after 22 seconds, we should have half of 20. So that'd be 10. After 33 seconds, we'd have 5. And after 44 seconds, we should have 2.5. That's half of 5. So you can see how with each interval here, like after 11 seconds pass each time, we're cutting the number in half. And so we already know what the answer is going to be. It's going to be 2.5 grams. But this one just kind of works out nicely because the number of seconds that has elapsed is a multiple of the half-life. It'd be a lot trickier, like if you're going to construct a table, to figure this out if the question was, how much is left after, say, like 45 seconds, right? Because that's not a full half-life. So you're not just dividing by some like clear, obvious number. So the way that we're going to compute this, I think, more generally is with that formula that I gave you. The 40 grams, that's your initial amount. That's going to be the A. The 11 seconds, that's the length of the half-life. So that's my H. 44 seconds is how much time has gone by. So that's T. So if the formula is F for the final amount equals the initial amount times 1/2 to the power of T over H. Again, that T over H is referring to how many half-lives have occurred. And we can see from the table there's going to be 4 of them, right? Now we can just start plugging in the numbers where they belong. So the initial amount was 40. So you have 40 times a half to the power of 44 over 11. And you can see how the 44 over 11 becomes 4. Again, this is computing how many half-lives have occurred. And we can see that in the table very clearly. So this is something that, if we couldn't figure it out like with the table, you just put this in your calculator. Okay, you do 1/2 to the power of 4 and then multiply that by 40. So we already know what the answer is going to be, but you could always double check that in the calculator, but we do get 2.5 grams. Any questions about example 1? All right, let's take a look at another example here. It says Astatine, I'm not actually sure how you pronounce that, has a half-life of 2 seconds. Okay, so that's my half-life. Let's go ahead and just mark that down as we go through the problem so that we're ready to fill in everything into our formula. Find the amount left from a 500-gram sample. So that's going to be our initial amount after 10 seconds. That's the time. So if we're just kind of thinking about how that formula is going to play out, 10 seconds are going by. Each half-life is 2 seconds. So the number of half-lives that occur would be 10 divided by 2, which is 5. Right? And we're going to see that happen in the exponent. So I'm going to rewrite our formula here, just sort of the generic A equals times 1/2 to the power of T over H, where the initial amount is 500. We're going to cut that in half, T over H, 10 divided by 2, which is 5 times. Okay, because the half-life is 2 seconds, and we're measuring this over the course of 10 seconds. 10 divided by 2 is 5. So, that's not always going to reduce nicely, but in this case it does. But we do need to put that in the calculator. Although 500 is that's a nice kind of clean, even number. We might just be able to cut it in half 5 times and get the answer. This one might be another good table problem. But if you've got a calculator, you might as well use it. So 500 times 1/2 to the power of 5. You should get 15.625 grams remaining. Now, if you're using these TI-30XSs and you type in the formula and it gives you the answer as a fraction and you're trying to get it as a decimal, just remember that if you press this little white button above the enter key, that's going to convert from fraction to decimal or vice versa. Any questions about example 2? All right, just have a few more here. Number 3. It's a blurry picture, but in 1999, archaeologists discovered the oldest bridge in England near Testwood, Hampshire. Carbon dating of the wood revealed that the bridge was 3,500 years old. Okay, that's going to be relevant to our problem. Carbon dating is a way to determine the age of very old organic objects. Carbon has a half-life of 5,700 years. Okay, so that's our half-life. Suppose that when the bridge was built, the wood contained 15 grams of carbon. So that's going to be our initial amount. And the question is, how much carbon-14 was contained in the wood when the bridge was found? So the half-life is 5,700 years, but the amount of time that has elapsed is actually only 3,500. Okay, that's our T. That means that there hasn't even been one complete half-life occurring yet. So, like if we started with 15 grams, but we haven't even completed one full half-life, that means that there would be more than half of 15 grams remaining. So if you go into this problem trying to compute your answer, you should expect there to be more than 7.5 grams as your answer. 7.5 grams would be if one full half-life has been completed. That would be a full 5,700 years. But only 3,500 years have elapsed. So again, we should expect a number bigger than 7.5. So we're going to set up that equation. T over H, okay? Start plugging in all of our values here. Our initial amount is 15 grams. And we're going to multiply that by a half. The number of times that the half-lives have occurred, which should be less than 1. So the t here, the time that has elapsed is 3,500 years, and the half-life is 5,700 years. So yeah, so this number is less than 1, right? Because less than 1 half-life has occurred. Looks like it's pretty close to a half, or no, a little bit more than a half. So yeah, we'll type this in. 15 times 1/2 to the power of 3,500 over 5,700. Oh, did I type that in incorrectly? Hold up. Yep, I sure did. Oh, no, that was right. Okay, so yes, approximately 9.8 grams. All right, I only have 2 more examples for you here. Hopefully this is kind of making sense. Really, I think once you realize that you're just plugging numbers into this formula, it's really not that hard. You just have to understand where everything goes. Okay, number 4 says iodine is sometimes used in thyroid scans and has a half-life of 13 hours. Okay, so 13 hours, that's our H. How much of a 200 milligram sample, that's our initial amount, would remain after 48 hours? So that's our T. So if we're thinking about in terms of like how many half-lives are occurring, if 1 half-life occurs after 13 hours, that means 2 half-lives occur after 26 hours, 3 half-lives occur after 39 hours, okay, and so on. So we're going to cut this number in half more than 3 times, but less than 4. All right, so let's plug it all in. We've got F equals our initial amount times 1/2 to the power of the total time divided by the half-life. So we are going to start with 200 times 1/2 to the power of, there we go, 48 over 13. Once again, this becomes a calculator problem, yeah? 200 times 1/2 to the power of 48 over 13, and I'm getting roughly 15.5 grams. Any questions so far? I mean, all these problems kind of get worked out the same way. Really won't be until we start like solving for T or solving for H that we'll really have a different kind of problem. We're not going to do that quite yet. Number 5 says one of the many byproducts of uranium is radioactive plutonium, which has a half-life of approximately 25,000 years. Okay, so that's the half-life, a very long time. If 10 grams, that's our initial amount, of this plutonium is encased in concrete, what fraction of it will remain after 100,000 years? So we're going to get the final amount, but then we also want to compare that to the 10 grams because the way this question is worded is asking what fraction of the original amount. So it should be like something out of 10. So it's going to slightly modify how we answer the question, but the overall process of finding it will be basically the same. So our final amount equals the initial amount times 1/2 to the power of T over H, which represents the total number of half-lives that have occurred. Our initial amount here is 10. The time that has elapsed is 100,000 years. It's a very long time. Over 25,000 years. So you can see that we're going to have exactly 4 half-lives occurring. Right? 25 goes into 100 4 times. So basically, we're going to take that 10 and just cut it in half 4 times. So you can almost do that in your head, right? Cut it in half once and you get 5, and then 2.5. After that, maybe you can't do that in your head. That's okay, but we're going to do that essentially 4 times. But if you don't want to do that by hand, that's totally fine. You can just type this in. And I think it's 0.625, but I just want to double check. So let's see here. And yeah, that's exactly what it is. So the final amount is 0.625. That's how much we have left, right? So this is the grams remaining. But the way this question is worded is kind of weird. I almost wish I kind of didn't word it like this, but it says what fraction of the original is remaining? So we got a fraction we basically have to set up here. So we have 0.625 is remaining, but that's out of the 10 that we started with. And your calculator can simplify this fraction. You don't have to do this by hand. But this is 1/16 of the original amount remains. Yeah, again, if you're using this calculator, you can just type it in as a fraction. It's going to give it to you as a decimal, but then you can just hit this button right above the enter key to convert it back to a fraction. So that's kind of the short and sweet version of this half-life stuff. Any questions?